Okay, I want to talk about the huge impact that Charlie and his students had on me personally, and also on my own students. In fact, my talk was begun by Saul Tucholsky, who was one of my own students and who described some considerable impact that Charlie had on him and his research program. I was a student at Caltech as an undergraduate, 1958 to 1962. And at near the end of my junior year, when I was beginning to ask myself where I might want to go for graduate school, I already knew I wanted to work in relativity. At age 13, I had read a book, 1, 2, 3, Infinity by George Gamow, the famous physicist cosmologist who had emigrated by forgotten swimming a river or fording a river from the Soviet Union some years before. And in there, George talked about how the laws of physics control the universe. And so I decided I wanted to understand the laws of physics. And the most exciting laws of physics he described were those of relativity, which controlled what I prefer to call the warping of space and time, or the curvature of space and time. And so I knew I wanted to work in relativity. I'd known it since I was 13 or 14 years old. And so I went into the Caltech library. This says my senior year. I'm now, I wrote that a while back. I've scarfed this off of an earlier lecture. I think it was probably late at the end of my junior year. But anyway, I went to the Caltech library and I read through a bunch of journals looking for research articles on relativity. And I remember, it's remarkable, I remember back that far. Now, this is like 60 years ago or so, but I remember quite vividly opening the Reviews of Modern Physics and an issue in July 1957, in which there were a series of articles. Although it's Reviews of Modern Physics, these were basically research articles by John Wheeler and people in his research group. There was this paper by Richard Lindquist and Johnny Wheeler on the dynamics of a lattice universe by Schwarzschild cells, was basically the title. He imagined a universe that consisted of nothing but black holes, what we would now call black holes. But he modeled them basically as the Schwarzschild geometry, and a bunch of them stuck together into a configuration that resembles a closed Friedmann universe. And he and Richard Lindquist, who was his student, I think, at the time, analyze the evolution of this. There was a paper by Joe Weber and John Wheeler on the reality of cylindrical gravitational waves. There was a paper by Power and Wheeler and another by Ernst. Power and Ernst were in his research group about geons. These were objects that were made from electromagnetic fields that were held together by the gravitational pull, or by the gravity that their own energy, stress and energy produced. And so there were toroidal geons in which he had a electromagnetic wave, and he's showing here, this is from the paper, he's showing regions of high intensity in the electromagnetic wave, and it's going around and around in a toroidal manner, and it produces a space-time curvature that holds the whole configuration together. There was a paper by Dieter Brill and John Wheeler on the interaction of neutrinos and gravitational fields, basically working out the theory of the neutrino field in general relativity, and basically how neutrinos behave in a generic curved space-time. Then John Clowder and John Wheeler on the question of whether or not you could have something like what John and Charlie Misner had been thinking about since somewhat earlier than this, a wormhole that was threaded by magnetic field lines or electric field lines, and so it would look like you had a positive charge at one mouth of the wormhole and a negative charge at the other mouth of the wormhole. And he asking the question, can the neutrino field support some sort of a structure in a universe that has a non-trivial topology, a structure like this? The answer was basically no for the types of structures they were exploring. There was the famous paper by Everett on the many worlds formulation of quantum mechanics, and then famous paper commenting on Everett's work. Again, Everett was a student in Wheeler's group, commenting on the many worlds formulation of quantum mechanics. And then there was the paper by Misner alone. You notice Misner is the only one who's not basically working directly on stuff that came from Johnny. The paper on Feynman quantization of general relativity that we just heard about. This is all in one issue of Reviews of Modern Physics. It was obvious to me where I wanted to go for graduate study. And that was reinforced by the fact that I was meeting Jim Hartle, who had just come as a graduate student. I was a senior undergraduate then, and this then was the following autumn. Jim Hartle had been an undergraduate working with Dieter Brill here in Wheeler's group on gravitational geons. I don't know, was the idea of a gravitational geon yours, or did it come from Johnny Wheeler, Dieter? Do you remember where did the idea come from? You don't remember what?
It seemed to be in the air.
It was in the air, okay. It was fairly obvious given electromagnetic geons. But the idea is that you had gravitational waves that were going around in a toroidal or other configuration whose energy density and stress of the gravitational waves was holding the whole configuration together. And in order to work this out, it was really necessary for them, for Hartle and Brill. So this is Jim Hartle here. Just a second. No, are those both Jim Hartle? I don't have you in there. I have two Jim Hartles. Isn't that right? I think that's right. I apologize. I have two versions of Jim Hartle in here. I don't have Dieter. I just grabbed these off the web. I screwed up. Anyway, they, in order to work this out, they had to develop what we call a two-length scale expansion of the Einstein field equations, and then do some averaging on it in a procedure that Richard Isaacson then, a few years later, as Charlie Misner's graduate student, took those techniques and applied them generically to develop geometric optics, a description of gravitational waves, and a rigorous discussion of the energy and the momentum of a gravitational wave, the stress energy tensor of the gravitational wave. And so Jim Hartle was there as a first-year graduate student, euphoric about his experience in this research group with Dieter Brill and with John Wheeler and with Charlie Misner. And so that just reinforced my decision. This is where I was going to go for graduate study. And so June 1962, I went to Princeton for graduate school, intending to work with John Wheeler and/or Charlie Misner. Charlie had been a graduate student working with John from 1954 to 1957. Before he actually defended his thesis, he was named an assistant professor in 1956. And so he was an assistant professor from 56 to 63 and then came here to Maryland. So I overlapped with Charlie for 1 year. And I didn't know when I went to Princeton that I was only going to have 1 year with Charlie. I presumed he'd be there longer. And so I was quite disappointed when he headed off to Maryland. But nevertheless, I got to know him quite well. And this also, of course, underlay our doing MTW together later. And then me, I went there for graduate school 62 to 65, and then one postdoctoral year there. And I had a euphoric 4 years at Princeton in the research group of John Wheeler. I want to say some words about the interactions between Charlie and John. And this goes back to the period when I was with them working on MTW a few years after my graduate study, but going all the way back to what I know about that in the period before I ever even went to Princeton, going back into the mid-1950s. Charlie had a superb mastery of mathematics. I understand from Benedicta that he got started by reading engineering textbooks of his father when he was a teenager. He taught himself calculus before he ever went to Notre Dame for college. And so he knew a lot of mathematics when he arrived at Notre Dame, to the point that there was no point in taking any of their undergraduate classes. And so he just took graduate courses in mathematics at Notre Dame while he was an undergraduate student. So he arrived at Princeton, a full-blown mathematician in terms of his mastery of relevant mathematics. And this very much impressed Johnny. Johnny was no slouch mathematically at all. I mean, he was deeply interested in the mathematics that could enable him and his research group to understand curved space-time, warped space-time, much more deeply than had been understood before. But just as an indication of Johnny's mathematical ability, I want to tell you a story about his relationship with Richard Feynman. Some of you may have heard this before. I've written it down on occasion. But Feynman and I were close friends at Princeton when I went back at Caltech when I went back there on the faculty. And we were at a party together, both a little bit inebriated, sitting off in a corner one evening. And Feynman confided in me the following story. He said he had this very painful experience once with Professor Wheeler, as he called him. And he always called him Professor Wheeler. By contrast with me, I had, the day after I defended my PhD thesis, I phoned up his home, Wheeler's home, and his wife, Jeanette, answered the phone, and I said, "May I speak with Professor Wheeler?" And she said to me, "Now, Kit, you defended your thesis yesterday. You may now call him Johnny." And so I would talk with Feynman about Johnny, and Feynman would talk to me about Professor Wheeler. Feynman described his experience of working on a calculation sort of side by side with Johnny. And he said, we got to some point where I could not understand how he got from here to there. And Professor Wheeler said to me, "Little steps for little people." And he marched through the intermediate steps. And this is the painful memory that Feynman had still decades later. And you can imagine what was really going on here, because I don't know that any of us ever saw Wheeler behave in such a arrogant sort of a way, particularly toward a student. But this particular student, Feynman, was extremely arrogant himself, particularly as a student, and it's obvious that he needed some putting down, and Johnny was doing that on purpose. Which, well, as I say, knowing Johnny, he must have really needed some putting down. But it was indicative that whatever they were working on, that Wheeler's mind in doing the mathematics was better than Feynman's was, at least on that particular instance. I also saw then this relationship between Johnny and Charlie then when we were working on MTW, on our textbook together. There are two chapters there, one on geometrization of Newtonian gravity using some mathematics that comes from Cartan, another on the Bianchi identity described in the language of a boundary of a boundary. Those chapters, I don't remember who wrote the first draft, but I do know that those were a combined effort between the two of them, going back and forth and back and forth. Deeply mathematical topics, but deeply mathematical topics that they also brought into a very intuitive form. And it was just marvelous watching the two of them together working on these kinds of problems. So I said that Charlie was superb at mathematics and Johnny was no slouch mathematically. Well, similarly, Johnny had a superb intuition, as we all know, and Charlie was no slouch in intuition either. I mean, these were things that really went into the success of our textbook together, is the kinds of combinations then of intuition and strengths of intuition in mathematics that they had. The major research foci of that period, the late 1950s and early 1960s, I got a sense of from a textbook that I actually have my own personal copy in my bag if anyone wants to browse through it. It's a book, it's not a textbook, it was a book that contained a compendium of papers that were written by Wheeler and Misner in the in the 1950s, and the book is titled Geometrodynamics, which was the title of the famous 1957 paper by Misner and Wheeler exploring classical geometry of space-time, exploring what the already unified theory of electricity and magnetism in vacuum, the fact that the Einstein field equations with electromagnetic fields present, the gravitational part of the field already contains full information about the electromagnetic field. It was something that Reinich had done at about the same time or slightly earlier. It was certainly the first to publish and got a Nobel Prize for it. But it was really discovered also by Charlie Misner and Johnny Wheeler through combined intuition and mathematical skill. So that was, geometrodynamics was a central feature that has remained for me the most exciting area of classical relativity through my entire career, and is basically what we are doing with LIGO these days, is studying geometrodynamics, the geometry of space-time of colliding black holes. There was the issue of gravitational collapse, and to form what nowadays we call a black hole, something that Johnny Wheeler gave the name to some years later in 1968. But at that particular time in the 1950s and early 1960s, John was paying zero attention to the horizon. He is focused solely on the issue of the final state, the singularity at the center, because if you had an implosion and it produces a singularity, that singularity is the place where you must have the fiery marriage, in his words, of quantum theory and general relativity that leads to the laws of quantum gravity. And so he really wanted to use this as a venue for exploring quantum gravity. And there, in fact, was this confrontation, a famous confrontation between Wheeler and Oppenheimer at the Solvay Congress in 1958, which I describe in Black Holes and Time Warps, which I know about partly from talking to Johnny, partly it's also in John, a little bit I think about it in Johnny's biography, but you have the proceedings of that conference where you have details of their argument. And it is when Johnny described research going on in his research group in that period, research that he was doing with Kent Harrison and Masami Wakano on collapse and on the equation of state of matter, of cold catalyzed matter, properties of neutron stars, and the implosion to form what we now call a black hole. But he was convinced that because a singularity appears to be formed, and you can't really have singularities in physics, that quantum gravity must come into play in some way and prevent the singularity from being formed. And he was speculating that something that resembles what we would now call Hawking radiation was coming off and would prevent the formation of the singularity. And so at the end of his lecture, Oppenheimer stands up and says, wouldn't it be much simpler than this wild idea of radiation flowing away and preventing formation of the singularity? Wouldn't it be much simpler if the black hole just cuts, if this configuration just cuts itself off from the rest of the universe, as he had found in his computation with Snyder, with Hartland Snyder? Isn't that much simpler, and isn't that what really happens? And Wheeler says, no, that can't possibly happen, because the singularity that's left there down inside is an anathema. And so they go back and forth. So Johnny did not believe in black holes in that sense, in that period. Instead, his biggest focus was on wormholes. And you see this in the famous paper of Reggie and Wheeler that has been discussed here before, in which if you read that paper, I suspect very few of you have ever read it, that we always regarded as the first paper on the vibrations of stability of black holes. But no, he doesn't think he's perturbing the black holes. He thinks he's perturbing a wormhole. Because the Schwarzschild solution, if you don't have any matter present, it represents a wormhole, not a black hole. And so throughout this paper, wormhole, 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 the word wormhole appears all the way through the paper. Collapsed star never appears. Nothing that resembles the concept of a black hole appears at all. But the word wormhole and then occasionally Schwarzschild singularity. And then you puzzle, what does he mean by a Schwarzschild singularity? He doesn't explain it in that paper, but you go back to the Bible of that era, which is Misner and Wheeler, the geometric dynamics paper, and in there you come to understand the Schwarzschild singularity, quote unquote, is the throat of the wormhole. It's R equals 2m. And he knows that this is not a real singularity, but he calls it a Schwarzschild singularity. So he's perturbing the Schwarzschild singularity, the throat of the wormhole, or he's perturbing a wormhole, but he's certainly not perturbing a black hole. And so I have written, there was after Tullio Reggi passed away, there was a book in his memory about his publications that was made, a sort of Festschrift book. And I have written in there a rather long article about the Reggi-Wheeler paper and the history of it. And I go into depth about this issue of perturbing a wormhole versus perturbing a black hole. Okay. Well, then, so the focus was on wormholes. The focus was on geometric dynamics, dynamics of curved space-time. Then 1960, much to, I think, Wheeler's surprise, Martin Kruskal, well, a little earlier than this, Martin Kruskal shows him more or less on a napkin a new coordinate system for Schwarzschild, which came to be called the Kruskal coordinate system or Kruskal-Zekarich coordinate system. And Wheeler then looks at the Schwarzschild solution in that particular coordinate system and describes the Schwarzschild wormhole pinching off as time passes. And now he suddenly understands that, well, wormholes cannot be static wormholes, at least if they're threaded by vacuum, they will have to pinch off. And so a whole new point of view about wormholes. And then Charlie Misner gives to David Beckendorf, a senior undergraduate, a research project to look at, re-examine the Oppenheimer-Snyder solution for the implosion of a ball of dust to form what we now call a black hole. The solution that John is completely skeptical about because of the singularity at the end of the point of the implosion. He gives to David Beckendorf a project, build this solution by taking a Friedman model universe made of dust and cut off a piece of it and attach it onto the Schwarzschild solution. And you should be able to get out of that the Oppenheimer and the Snyder solution, and indeed he does. Now, as background on this, let me say the following. Yevgeny Lifshitz, who was a close personal friend of mine in Moscow, when I first went to Moscow in 1966, I think it probably was, no, it was 68, and really got acquainted with Yevgeny. He described to me how terribly difficult it was to understand the Oppenheimer-Snyder paper when that paper came out. And the Russians were just reading the paper. They didn't have Oppenheimer to talk to. They just had the paper to read in physical review. And they could see the viewpoint of the distant observer. This star shrinks and then it freezes at the Schwarzschild radius. It freezes at what we now call the horizon. But then you could also look at the mathematics, and it was obvious from the point of view of somebody sitting on the star's surface, that person goes in finite proper time on through and hits the singularity. And how do you reconcile those two different points of view? And this is a quote from Lifshitz. You cannot appreciate how difficult, by you he meant physicists of your generation, he says to me, cannot appreciate how difficult it was for the human mind to understand how both viewpoints can be true simultaneously. Just totally impossible to understand. And it was Beckendorf and Misner who explained it. How is it possible to be true simultaneously? And this is the figure from Beckendorf's thesis. You can get his thesis online. Here you have a piece of the Friedman universe, and you have a piece of the Schwarzschild solution in embedding diagrams, and you just match them together at a join point. And he then does the mathematics, and that smooth match just holds together. Once you've made the match at some initial moment of time, it works all the way through the implosion. And I first learned about this when I arrived at Princeton, September of 1962. Beckendorf had done his thesis the preceding autumn, or preceding spring. He presented his thesis. And Charlie gave a seminar about this. It was the first seminar I heard, as I recall, in 1962. And he just described this. And it was just so beautiful. And it was just so obvious. And it was an epiphany. And it just transformed how people, I think, in Wheeler's group were thinking about the subject. And suddenly, then, that was the basis for gravitational collapse to form a black hole being, I think, accepted in Wheeler's group. Now, see, how much time do I have? Just let me know. 5 to 10 minutes more, okay. Let me say a few words about foundations of numerical relativity. 1957, Johnny Wheeler was, beginning in 57, Johnny Wheeler was giving exhortations to his students and postdocs and colleagues that you should explore geometric dynamics. This is a photograph of Johnny up here giving a lecture on geometric dynamics at a birthday symposium for Willie Fowler in England. You should explore geometric dynamics through numerical relativity because it was so difficult to study generic geometric dynamical phenomena analytically. Of course, the foundation for doing it via numerical relativity was in the work of Arnaud, Desir, and Misner, which we've already heard about today, the ADM work on the 3+1 decomposition of Einstein's equations. And the initial conditions for the first geometric dynamical numerical relativity calculation were given by Charlie Misner in a paper we've already heard mentioned today on wormhole initial conditions, not initial conditions for two black holes colliding, initial conditions for the mouths of two wormholes to collide. So you go read this, and it's all about wormholes the mouths of two wormholes colliding, has nothing to do with black holes, has nothing to do with gravitational collapse. But this is 1960. This is before the epiphany about black holes. The actual first calculations then were done by Richard Lindquist, whom I mentioned before, together with Susan Hahn. Lindquist by then is a postdoc, but he's gotten started on this, I think, under the influence of Johnny Wheeler. Susan Hahn was a superb computational physicist at IBM. And unfortunately, I've never found a photograph of Susan Hahn, and it's one of the sadnesses historically from my point of view, because I think this is a tremendous important paper, the first attempt to integrate Einstein's equations, the evolutionary equations for the head-on collision. They could not get it all the way up to the collision. The computer crashed before they got it all the way up to the collision. And that was later done under the influence of Bryce DeWitt by Epley and Smarr a few years later. But Epley and Smarr were building on this. And the key thing that is going on here is that outside of the horizon, which means outside of the throat of the wormhole, this is just a black hole and that's just a black hole. The fact that they connect together in the interior is not known outside the horizon, so it's not known in our universe whether the interior is the interior of a black hole or whether the interior is a wormhole that is hooked up together. You just don't know. And so by the time this calculation is being done by Epley and Smarr, a decade or so later, they're using the words black hole, but they're doing the same computation as Hahn and Lindquist were doing when they thought they were imploding the two mouths of a wormhole. This really was the true birth of numerical relativity. And well, Saul can tell you the rest of the story, but it is, I think, really remarkable to me how this grew out of the geometric dynamic vision that Johnny and Charlie developed in their research group. I want to say in conclusion, I think I have other things I could talk about, but I think I'd like to say a few words about the writing of MTW. I gave a rather detailed discussion of this in a celebration of MTW called MTW 50 that we had a few months ago, and you can find the video of that celebratory thing online. I talk about the making of MTW, and Charlie makes some additional concluding remarks just not long before Charlie passed away. And you see how vigorous he is despite being on hospice with terminal illness. He was just full of life, and it was just so inspirational doing this with him. The period when we did most of the work on this textbook was summer 69 and summer of 1970. This was our intense, near 100% effort on the book during that period of something like 20 months that led to the first preliminary edition in September of 1970. Of course, the book didn't come out till 73, but the big push, the huge push was summer 69 to summer 1970. And we agreed whenever any two of us expected to be together, the third was obligated to try to join, at least for a few days. And so we met and we wrote, we revised, among other places, in Princeton, at the Institute for Advanced Study in the University of Maryland, Caltech, University of Texas in Austin, National Airport in Washington, D.C. It was one of our favorite places to meet because I could just fly in and sit there and work with them for half a day and then fly back home. Dublin, Ireland, Kyoto, Japan, and in the USSR, in Moscow, Kiev, and Leningrad, and in Maine. A lot of time spent in Maine together. And it particularly memorable was the summer of 1970 in Maine. John and Jeanette, his wife, owned half of High Island here. This half down there, and the half up north was owned by, I forget who owns the other half? The Sheldons, that's right. The Sheldons own the other half. And so Johnny's home was here. Charlie and Susanna had a home here, and my wife Linda and I and our children rented a little cabin called the Crow's Nest here on McFarland's Point. And the total distance here is about 1 kilometer. And so we could happily walk up to John's place to work together and back, or drive. And it was just an idyllic summer. This was the view from Charlie and Susanna's home, looking out onto the bay, the ocean in Maine, this lovely, beautiful indented coastline. Johnny and Charlie together, Susanna, Benedicta, Francis, Tim, and Chris were all here except Chris, who's not able to be here today, but I was exchanging email with him yesterday. He was apologizing he couldn't be here today. But the other three are here. Me, my wife Linda, Brett, and Karis, our children. And it was just, as I say, idyllic, exciting, and very, very intense work together. For each chapter, one of us wrote the first draft. We circulated the chapters to each other, and there were at least 3 times around on essentially all chapters. So we were writing and rewriting each other until they converged. And for many chapters, you will not guess who wrote the first version. So, and then we would send it out. Whenever the manuscript got too messy, we would send it out for typing and then continue working from that typed version. Charlie wrote the first draft of the chapter on gravitational waves. And this is the front of his first draft. And his first draft had a huge impact on me and how I think about gravitational waves. I mean, just a tremendous impact. Before that draft, I thought about gravitational waves in a much more, well, just flat space-time sort of a way, linearized theory. I didn't understand things in any depth at all. And it was just transformative to me reading Charlie's first draft. And part of that was Richard Isaacson's PhD thesis on geometric optics of gravitational waves and the gravitational wave stress energy tensor, which is built on the work of Dieter Brill and Jim Hartle. Well, I wrote the first draft of the chapter on global methods. You would never guess that, but I wrote the first draft. Charlie rewrote it. I assure you he wrote it. But that's another example that you wouldn't guess who had written what. Here is an example of Charlie rewriting me. So a bit of John's writing. Then I've rewritten John's stuff. And then Charlie is down here rewriting me. And that is a not atypical page that went to a typist. First preliminary edition, September 1970. And the dedication, this is really an important thing to me. The dedication is very precious. And how did it come about? Well, Johnny wrote a letter to Charlie and me, 25th of January, 1972. I would like to take, and this is his words from this letter, I'd like to take up and expand on a theme that you sounded, Charlie, at the end of your chapter on mixed master cosmology, about the interest of the public in science. I must say I am upset every time intellectuals set themselves up on a pedestal as objects of worship, rather than as servants of the larger public. In that vein, he proposed the following dedication. This book is dedicated to the humble old lady sweeping the walk with her broom, the eager child, and all who, with their love of truth, take from their own wants by taxes and gifts, and now and then send forth a dedicated servant out of their number to forward the search into the mysteries and marvelous simplicities of this strange and beautiful universe, our home. In response to this, Charlie and I had a conversation, and I write to John, as I sat outside with our son on my back all weekend, I kept thinking of you standing facing into the sun on the shore of the Gulf of California 2 years ago when we were riding together. We'd gone to Mexico to ride together. Charlie and I, we'd had an intense conversation about this, would like to propose a little change in the dedication. We feel that the point of the dedication would come across more forcefully as the first 4 lines were deleted. It was just a little bit too much, we felt. And so the humble old lady sweeping the walk with her broom and the eager child are gone. And our final dedication to all who with their love of truth take from their own wants by taxes and gifts, and now and then send forth a dedicated servant to their number to forward the search into the mysteries and marvelous simplicities of this strange and beautiful universe, our home. So that was our final dedication on this book. And I think I should quit and give other people a chance to talk. As I say, I could go on and on. I've talked about a tiny fraction of Charlie's impact on me. But my personal relationship with Charlie and the relationship the three of us had working on MTW, the things that I learned from Charlie and the friendship, an emotional friendship that we shared are just of enormous importance to me, as a treasured part of my life. Thank you.
This is an easy one. So you probably remember Probable, Possible, My Black Hen. She lays eggs in relative when she doesn't lay eggs in the positive now because she's unable to postulate how.
Yes, I remember.
So where does that come from?
It's the space child's Mother Goose. And I don't remember who the author is, but it's a wonderful, wonderful little.
I mean, I just want to say thank you for this book. I can't thank Charlie or Wheeler, but I can thank you. That book of all the books that I've ever read, that had the most profound effect on me, both in the clarity and the poetry of it, and the combination of the two, and the physics, without losing, pardon my French, without bullshitting your way through some part of it. I think that was just an amazing accomplishment and should ring down, and still rings down through the ages, though, of course, it's really long.
It's really long. Let me make just one further remark about that book, which wasn't in here, but I think is still worth making. In about 2014 or 2015, I discovered that it had gone out of print. And it was in the hands of who's the publisher begins with M-I-L? Macmillan. It was in the hands of Macmillan. Macmillan had swallowed somebody who had swallowed somebody who had swallowed Freeman, who was the original publisher. And Macmillan had classified it as chemistry and put it in their chemistry catalog. And they were having a little bit of trouble selling it out of their chemistry catalog. And I don't know whether that was the only cause of this, but basically the book was taken out of print. And so many of you may know Bruce Winstein. Bruce is my brother-in-law. He was my brother-in-law, passed away a few years ago, a physicist, an eminent physicist who worked in high energy physics and cosmology. Bruce's widow, Joan, took on the task of prying the rights out of the hands of Macmillan and getting it back to Johnny's estate, to Johnny's children and Charlie and me. She pried the rights back, and we turned it over to Princeton University Press, who published a new edition. And since then, it's been selling several thousand copies every year. So by now, it's sold something like 20 or 30,000 copies since it went out of print in the hands of Macmillan. It's just amazing how much even the current generation is still wanting to read it. It's really been lovely to see. So, yeah.
As someone that's not an expert in gravity, I didn't quite get the answer. So there was a wormhole, or there was a collision of two black holes. Do we know now from the LIGO experiments which one it is?
It's impossible from outside of this object to know, because the wormhole, this particular wormhole, has a horizon, and outside the horizon, its geometry of space and time is identical to that of a black hole.
And even after the collision, there's no signature of which one.
Not outside the horizon.
Okay, very interesting. Thank you.
Horizon. So, yeah.
Hello. So yesterday I learned that gravitons are solitons and have a
black holes are solitons.
Black holes are solitons. I'm sorry. Do geons? I've never heard of geons before, but what makes them unique? Do they also have a soliton waveform?
So geons are objects that Johnny Wheeler discovered as solutions of the combined equations of general relativity and electromagnetism. They hold themselves together temporarily, but he evidently understood practically from the beginning that there would be leakage, and the electromagnetic waves or gravitational waves that are providing the energy and momentum, that density that hold the object together, that through their gravity, that these waves will gradually leak out. And so they can't live for a terribly long period of time. He understood practically from the beginning, I think, that the geons then were not objects that you could expect to find in the real universe. But they were objects that played a key role in teaching us that there is a great richness to geometrodynamics. There's a great richness to the kinds of things that warp space-time can do, even if you don't have any matter present. And that was what he was discovering together with his students and postdocs in the 1950s, is this great richness that nobody previously had imagined. But as I say, the geons were not something that he thought that you would ever see formed in the real universe. But they were very powerful pedagogically for him and for his research group, his colleagues, and his students.
So I first learned of Mach's principle when I was an undergraduate student. This whole idea of matter here affects inertia there. But every time I kind of delved into like the literature and online, like I always got a sense that we don't really understand inertia yet. Like, is it true that we understand the origin of inertia like fully?
Let me say, I don't understand the origin of inertia fully. There may be others among my colleagues who do, but I don't.
So you were talking about how the gravitational wave chapter was originally written by Charlie Misner, and then that really shaped your thinking about it. And then you went on to do a bunch of stuff with LIGO, and I was just wondering, did Charlie Misner also influence your thinking on LIGO, or how did your paths diverge there?
He was very influential on my thinking about gravitational waves themselves. Early on, when the focus was on Weber-type gravitational wave detectors, he introduced the concept of a gravitational pulse unit, which turned out, GPU, which turned out to be a very powerful and simple way to quantify those aspects of the strength of the gravitational waves that one sees if one can only see burst and recognize that the burst is there and can't see the full details. So he was sort of in the mix of what people were doing also on the experimental side because of his interaction with Joe Weber. But by the time we got into doing interferometry and moving in the LIGO direction, he was not involved in that. His personal focus was elsewhere. But he really was the person who taught me about gravitational waves. If you read that, just say the first gravitational wave chapter on propagation of gravitational waves, you'll see that it goes ever so far beyond just treating the so-called linearized approximation of gravitational waves. That you see first in terms of exact solutions of Einstein's equations for plane waves. You see the energy and the momentum in the gravitational wave showing up in an exact solution in a way that you can really quantify exactly. And then he does the transition over to a more realistic gravitational wave that's not a plane wave, and how the Isaacson stress energy tensor then picks up what you were seeing in an exact solution and carries it into this generic domain. He just talks about the dynamical degrees of freedom in the gravitational wave in a very deep sort of a way, and how they're associated with the so-called transverse traceless part of the field. All of these things were things that I knew virtually nothing about until he presented me with that first draft of that chapter.
Out of all the discoveries LIGO has made till now, what's been the one which has fascinated you the most?
I think the thing that fascinates me most about LIGO's discoveries is the fact that the waveforms match so beautifully those from the simulations of black hole mergers. And in the numerical simulations, we see this very rich dynamics of warp space-time. We see the geometric dynamics. And then to me, the question is, to what extent then can we, from the observed waveforms, verify for sure that the geometric dynamics is like what we're seeing in the simulations, and the beginning to get a better handle on that through the overtones that in the simulations that Saltykowski talked about, And so, but this is my particular interest. I think for other people, there are other aspects that are of greater interest, such as the neutron star collisions and the evidence that gold and platinum are made in those collisions. But my personal love is geometric dynamics, and so it's seeing geometric dynamics in the real world.
Your last comment just triggered something I've been wanting to ask. So I remember when LIGO was being developed and planned, the guaranteed signal that made it worth spending so much money was neutron star coalescence, because we knew that there were binary neutron stars in some kind of a population. It turned out that the number of those events is extremely small, and almost everything that LIGO Virgo has seen is black holes. So the question is, did you anticipate or dream of ever or know of any discussions of this possibility before it happened, that it would turn out to be lots and lots of black hole coalescences?
Well, I myself thought that more likely than not that what we would see would be what we did see, black hole mergers. And I gave my own exhortations to my students and postdocs that they should pay attention to that, and to Saul and others that they should really focus on getting the black hole mergers going because of that. But I did not, I've been trying to figure out why do I not find this, that I clearly remember that I was making this prediction at the time, in why is that not in my writings? And we'll discuss this in our next LIGO history meeting. Peter Shawn and I, with Peter Fritschel and Ray Weiss and Barry Barish, are writing a history of LIGO. And this is a current issue. So it turns out I had a long email exchange with Ana Flanagan and Scott Hughes, and they reminded me of what I had really forgotten, or maybe consciously erased from my memory. I was so burned by John Bacall and Tony Tyson accusing me of selling LIGO on the basis of unrealistically high estimates of the strength of the waves, that I was not willing to go out and say what I really believed about this. So I was just telling my grad students and postdocs and colleagues, and I have emails and memos to this effect, that they really need to be paying attention to this, because this is likely to be true. And I got Scott and Ana to assert that this is true without attributing it to me in their classic paper that they did on black hole mergers. Certainly that was what was in the wind in our discussions, but not what I was saying publicly. It turns out I didn't even remember I wasn't saying it publicly until just yesterday, when I had this email exchange with Ana and Scott, and in which I had said explicitly, I've been burned by this, and I won't say it.
If I can just echo something, though, I mean, this had actually real practical effects, because the people inside LIGO at that time were paying attention to all the predictions of the neutron. There's going to be neutron stars would be the signal. It was going to be a very weak signal initially, and that a lot of the discussion was about they didn't want to get burned by having some weak signal and claiming it was a real detection, and then have people argue about it. So what was going to be the criterion to publish that they had seen something? And partly inspired by Kip, I had discussions with people like Alan Weinstein, people in the LIGO collaboration at the time. You shouldn't pay attention to what the theorists are saying are the event rates. You're an experimentalist. I mean, I'm a theorist. I had to tell him, you should be, if you don't look for something, you won't see it. What if it's big black holes? And I remember his response. He said, oh no, it's not going to be big black holes. And anyway, he said, we don't have the person power to spend our time preparing for something that's not going to happen. We know it's going to be neutron stars. We have to focus all our efforts on making sure we can do that detection. And when the signals were first detected, and it was big black holes, they were completely unprepared for this inside. They didn't have waveforms that.
Well, you had waveforms.
Well, no. I mean, the LSC itself did not have as part of its pipelines a method to analyze the signal is, it's very little in spiral. It's all the merger practically. And the models at that time were not very reliable for doing those things. And this caused, I mean, there's a long delay. There's 5 months between the discovery and the appearance of the paper. And in public, the reason for this is because they wanted to be sure and make sure it wasn't a hoax and so on. But my personal feeling is the real reason was lack of preparation because they had expected to be neutron stars.
Well, so Peter, will you respond to that? Peter was really the lead data analyst on LIGO. He's head honcho.
I don't think that explains the 5 months, because there was actually a remarkable sequence of internal steps for validating the detection, and I don't think it was especially lengthened by less familiarity or less experience with doing like parameter estimation on this. But it's certainly true. I mean, a lot of what you say is true, that there was definitely, at that point in the LIGO scientific collaboration, there was definitely a very strong bias, collectively at least, toward binary neutron stars, to the extent that the low latency analysis that was being done, the rapid analysis that was being done to search for binary mergers, was only for low mass events, such as binary neutron stars. There was not an immediate search being done for objects of the masses that in fact merged on that day by the matched filtering, the compact binary coalescence group. It was only found rapidly because of our more general search for arbitrary signals, which took a much more agnostic view.
We were lucky that it was such a strong signal.
Yes, that's right. If it had been marginal and detectable by matched filtering, but just at the threshold, we wouldn't have caught it on that day. It would have been a year later or something like that when the actual search was done later. So, I mean, there are a combination of factors, but that bias was definitely there, at least in a collective sense. Oh, I was going to say, though, just as a different kind of wrinkle on that, I remember that there was an NSF review that was held at Caltech. I don't remember the year, but I was sitting in on one of the sessions, and Vicky Caligera was in the position of advocating the expectations on the astrophysical expectations for signals and all that. And my memory of that session was that she was emphasizing what was known about the binary neutron star rate based on the observed binary neutron star systems, as was her scientific kind of focus But the sense of it, I think, was that the binary neutron stars are almost certainly present. I mean, they're less likely to be negligible. They're more certainly non-zero or more certainly not negligible than the binary black holes, because there are certainly estimates of the rates of binary black holes that would allow them to be at high rates. It's just that the uncertainties were considered larger.
Might be on already.
Hello? Yeah. I was going to make the same point that.
This is Richard Isaacson, as you may know.
At NSF, we had to sell a project. And, while I would have discussions with Kip and all sorts of spectacular sources like spinning pairs of black holes and so on were there, and we suspected they would have a big signals. You can't go to the science board because you can't calculate an event rate in advance for these things. But with the neutron stars, there actually was some astrophysical study, and you could say that these were the gold-plated sources, that no speculation. Here's what scientists say the event rate is likely to be, and we expect that we're going to see those. If we get extremely lucky, there may be much stronger signals. Maybe the initial LIGO would have even seen something. but no matter what, we're going to see neutron stars. So I think that's why they played a significant role there.
Hi, yes. I have a question about the sort of looking forward at the future of gravitational waves in terms of detection. I was hoping to get your comment on some of these other experimental techniques, which some of them are being built like atom interferometers are being, I think, underway, being constructed with claims to potential to detect gravitational waves. And also people have talked a lot about using atomic clocks, maybe connected over a long baseline in space. Do you have any comments on any of these you find exciting?
Let me just say that these may have long-term applications and may turn out to take over the field in the long term, but not in the next decade, and probably not in the next 2 decades. Actually, turning an atom interferometer into a gravity wave detector is sufficiently challenging, and it's going to require sufficient level of effort to really pull it off. That I don't think it's going to come quickly, but I think it could well come, and it could well be the dominant way that people are doing it in at some point in the future.
I apologize, but I think we have run out of time. So we just thank Kip again for a great talk.